do I get to see myself, Frank, or not?
You should see yourself.
All I'm seeing is PowerPoint. There we go. Just making sure. Hello, my name is Dr. Janet Shiver at Central Washington University. And today we're going to be looking at linear functions. We're going to start with a quick review. All right, if you'll remember from your past math courses, a linear function is one that repeatedly and at even intervals adds the same value to the output. In other words, you're adding the same amount to each output value every single time. When you graph these values, you end up with a line, hence we call them linear. Algebraically, a linear function can be written as f of x equals mx plus b. This is the slope-intercept form of the equation, and it just happens to be my favorite, so this is the one I'm going to stick with throughout this lesson. If you'll remember, m is your slope, or what we call the average rate of change, and b is your vertical axis intercept. I'm going to refer to it as the vertical axis intercept instead of the y-intercept because oftentimes your variables don't involve x's and y's. They might be a's and b's or p's and q's. So they'll be referred to as the vertical axis intercept. All right, if you'll remember, slope is defined as the change in the vertical divided by the change in the horizontal. Or a lot of you have probably heard it said rise over run. And if you recall, the equation for solving for slope is y2 minus y1 over x2 minus x1. So we're going to begin with a quick example to remind you of how to solve for a linear equation, how to write one. So let's take a look over here, and we're going to look at this circus tent problem. The outside wall of a circus tent depicted in the figure is 10 feet high. 5 feet toward the center pole, the tent is 12 feet high, right here. The center pole of the tent is 60 feet from the original outside pole. All right, the first thing we're going to do is we're going to determine the slope of the roof line for this particular tent. To do that, I'm going to gather 2 points. I'm going to take the outside point right here, which occurs 0 feet from the outside, and the wall is 10 feet high. So there's my first point, 0, 10. My second point I'm going to find is when I go 5 feet in, it's 12 feet high. So there's my second point, 5, 12. To write the equation of a line, you've got to have slope and you've got to have intercept. So let's start by finding the slope. M is equal to 12 minus 10 over 5 minus 0. So the slope of my line is going to be 2/5. Okay, that's something that you probably already knew how to do. One important thing, though, that I want to point out is that you need to be able to interpret that value. What does 2/5 mean? It's great to get a number, but if you don't know what it means, it's kind of useless. So let's look at 2/5. When you interpret a slope, you always interpret it in terms of y's per 1x. So in other words, in this case, my y values represent the height of the tent, and my x values represent the distance from the outer pole. So 2/5 would be interpreted as an increase, since it's positive, an increase of 2/5 feet, and this is going to be vertical feet, so an increase of 2/5 feet per 1 horizontal foot. So for every 1 foot I go horizontally, my tent is rising 2/5 of a foot. All right, so now we're going to write our model for our equation here, down here, for the slope of that, or for actually the line that's following the roof line of the tent. To do that, I need to find the y-intercept. Well, we often refer to the y-intercept, or the vertical axis intercept, as our initial value. How high was the tent before you started moving toward the center pole? Well, it was 10 feet. So there's my intercept. Putting that into our equation, f of x equals mx plus b, we get f of x equals our slope, which is 2/5, x plus 10. There we've got our linear equation. Now I can find anywhere along this horizontal, I can find how high the tent has risen. Okay, so let's do it, just practice one more of those. Use your model to find the height of the tent at its center pole. Well, the center pole is 60 feet in, so let's use our equation and just plug in. We are looking for f of 60. I read that as, when I'm 60 feet along the horizontal, how high is this pole going to be? How high is the roof line? So plugging in, we get 2/5 times 60 plus 10. All right, we get 2 times 12 plus 10, 24 plus 10, and my answer is 34 feet. All right, that's a quick review of what we've already learned about linear equations in the past. What we want to do now is take it and look at something called linear modeling. What happens with a real data set, real data from the real world? How do we address that? So we're going to start with a little example, and this example involves a bird. And let me pull him up right here. All right. There once was a thirsty blackbird who found a pipe with a small amount of water in the bottom. He tried to drink from the pipe, but unfortunately, his beak was too large to fit in very far. How could he get a drink? If he tipped the pipe, all of the water would spill onto the ground, and he would still be thirsty. After thinking for several minutes, the bird noticed that there were several small pebbles lying on the ground around his feet. He decided that if he threw the pebbles into the pipe, the water would rise and then he could get a drink. And you can see clearly that the bird was very successful. Now, the reason this bird was so successful was because there was actually a worm floating on top of the water, so he was a little more motivated to get his beak in there. So let's pretend that we have gathered some data on this bird. And let's just pretend, because this is in pretend math world right now, that this is the data that we gathered. I'm going to be using marbles instead of rocks like the bird did, but let's just pretend those are pebbles. When he started, that water, let's say, had a volume of 30 milliliters. So at 0, he had 30. And with every pebble he threw in, the water increased, as you see right here. 32, 34, 36, etc. First thing I want you to notice is that this data does represent a function. Why is it a function? Because for every input, there's exactly one distinct output. For 3 pebbles, there's 1 volume. There's no more than 1 volume for that. Now, remember what we learned about just a minute ago about linear functions. Linear functions are one that repeats evenly for every y value, so that output is going up evenly. So to check for data sets, to see whether or not they're linear, we can check something called the first differences. This is where I check to see if the y values are increasing by the same amount every time. All right, first thing though you have to check before you do that, make sure your x values are going up evenly. It doesn't make any sense to check the y values if the x values are scattered. So let's check our y values here, simply by subtracting. 32 minus 30, 34 minus 32, 36, 34, all the way up. I can clearly see that my value is 2. It's increasing by 2 milliliters with every pebble that the bird added. All right, now what I want to do for this then is take and write an equation. Again, using the same model that we used before, f of x equals mx plus b. So for this data, I can see that we're increasing by 2 every time, and an increase of 2 is my average rate of change or my slope. So f of x equals 2x plus b, again, remember, is also referred to as the initial value. How high or how much water did I have at the beginning of this experiment? Well, I had 30 milliliters. So when x is 0, y is 30. So my initial value or my y-intercept is 30. Okay. Also, don't forget to define your variables here. X is the number of marbles, in this case, or pebbles added. Or we'll just say number of marbles. And then our f of x value is the volume of the water in milliliters. Okay, this was a great problem. It works beautifully. However, in real life, data is seldom perfect. It never turns out where it increases by exactly 2 every time. So what we need to do is take a look at some data that doesn't increase perfectly. I always call these problems my Math World problems, because in Math World everything's perfect. But we're going to take a look at some that is not so perfect. So let's take a look at the total federal education expenditures by the United States from 1985 to 1989. All right, the first thing we're going to do is we're going to create, well, first of all, on second thought, let's go back. First thing I want you to do is pay attention to your x values. Are they increasing by the same amount every time? Well, the answer is probably yes. All right. If they are, then we can check those first differences to see whether or not this data set is linear. So at this time, if you would like to do it on your own, take a minute, stop the video, and calculate all of your first differences. All right, now that you've had an opportunity to calculate them, let's take a look at what you got. All right, I got 1.1, 1.3, 0.8, and 0.9 billion dollars as the changes in my y values. Clearly, that's not perfect. Okay, so I can't say that this data set is perfectly linear. However, I can say, these data values are pretty close, these first differences. So I think it might be linear. So we're going to have to find something else to help convince us that a line may still fit this data best. So let's take a look, and let's go ahead and graph this.